In this video we explain the concept of electrolysis. Until now, in all of our studies of electrochemistry, we have leveraged redox reactions to obtain galvanic cells. In a galvanic cell, the redox reaction occurs spontaneously, and then you can get an electron flow that can be used to do electrical work. Here we have a textbook example of a galvanic cell in which we're running this reaction. In the cathode, which is the reduction, we have copper 2 plus reducing to copper. Okay, that's what happens here. And then there's 2 electrons that are transferred, that are accepted by the cathode from the anode. Okay, and in the anode you have the oxidation of zinc to zinc 2 plus, which releases 2 electrons. Those 2 electrons go to the cathode, where you can then reduce copper 2 plus to copper. Alright, so when you look at the standard cell potential of that Daniell cell, that's 1.10 volts. It's positive, which means that this process will happen naturally. Now, electrolysis is exactly the opposite process to a galvanic cell. Right? The idea is that we're actually going to run this reaction backwards, okay? But of course, if we do that, then the standard cell potential will be negative, the same magnitude, but with a different sign. And what that means is that the reaction will not take place spontaneously. Okay, so let's then try to draw how that would be. So this is a galvanic cell, this will be an electrolytic cell, and then the reaction is going to be just backwards, right? So you will have that copper with zinc 2 plus will generate copper 2 plus zinc. And again, when we look at the standard cell potential for this reaction, that will be equal to minus 1.10 volts. All right, and what that means is that now your cathode is here. That's the reduction. And this is where the anode is. And this is where the oxidation takes place. All right, so now we have that zinc 2 plus is reducing to zinc, so zinc is being plated onto this electrode. And then copper is going to copper 2 plus. Okay, so that is what's happening at the anode. All right, great. So this is what we call an electrolytic cell. Now the question is, well, how can we make the reaction happen if the standard cell potential, or the cell potential, if the concentration of ions would be 1 molar and 1 molar is negative? Well, you can still make this happen. But you need to do some external work, right? So the idea is that this will be a non-spontaneous process, but you can make it spontaneous if externally you add enough work to reverse the process. Okay, so that is exactly what we do here, right? What we have is that we're going to couple this now to a power source whose voltage has to be larger than 1.10 volts, right? If we do that, if we add electrical work by external power supply that supplies more than 1.10 volts, in principle we can reverse the reaction and then run it backwards. Okay, so now electrons will actually go this way. That's what that power supply is going to do for you. It's going to be able to reverse the direction of the electrons. Now, these electrolytic cells have many applications in real life. For example, the way we obtain aluminum, which is a very common metal used in a variety of infrastructure, okay, is actually through electrolysis. We simply take aluminum ore and then we electrolyze it to obtain pure aluminum plated onto some electrodes. Okay? Now, something that is important about these electrolytic cells is that we have full control on how much current we're actually supplying through that power source. And if we know how much current we're supplying, then we can actually run stoichiometric calculations. Okay, so the idea here is that in this reaction we're plating zinc onto this electrode, right? So those zinc 2 plus ions are being plated onto that zinc electrode. We can actually calculate the mass or the moles of zinc plated if we know the current that we're supplying and how long that current is being supplied for. Okay, so let me show how those calculations would work. I'm going to erase here the details of the galvanic cell, right? What we have here is that current is simply charge per unit time. Okay, so the units are going to be amperes. Okay, it's going to be coulombs per unit time, which is going to be seconds. Right, so we're actually going to do a numerical example to illustrate how this electrolytic cell would work with stoichiometric calculations. Okay, so suppose that we're able to supply a voltage that is larger than 1.10 volts, and the current that we're supplying is 10 amperes, which is the same thing as coulomb per second. Okay, and we're doing this electrolysis for 30 minutes, right? So time, this is the current, and then time is going to be 30 minutes. The question is, what is the mass of zinc metal that we have plated onto that zinc electrode? Right, so the idea is that with this information, we can actually calculate the number of electrons and the moles of electrons that we have supplied to this electrolytic cell. And because for every mole of zinc that you need 2 moles of electrons, then there will be a stoichiometric calculation to relate charge, the current that you're supplying, to the mass of zinc that you're plating. Okay, so let's go a little bit slowly to see how this works. Right, the first thing that we can actually do here is calculate what the charge, how many electrons, or the charge that we have supplied to this electrolytic cell. Right, so our charge is going to be the current, which is 10.0 coulombs per second, times the time over which we have supplied this current, which is going to be 30 minutes. In seconds, that is going to be 1800 seconds. Right? So when we do this, it turns out that the charge that we have supplied is 1.80, 10 to the 4 coulombs. Now, this is charge, but we would like to relate this to electrons, ideally moles of electrons, because that is what intervenes in our stoichiometric calculations. All right, so how do we do that transformation? Well, that is what Faraday's constant gives you, because Faraday's constant tells you what is the charge supplied by a mole of electrons. Right, so if we take this charge, 1.80 10 to the 4 coulombs, and then we divide over Faraday constant, which is 96,485 coulombs per mole of electrons, then this will give us the number of moles of electrons that we actually have supplied. Okay? And then, if we have the moles of electrons, again, we can go back and take a look at the half reaction, which would be zinc 2 plus 2 electrons to generate zinc, and then be able to find out what the moles of zinc would be. Right? So again, notice that this calculation will give us the number of moles of electrons, and then I can cross the stoichiometric bridge to find out how many moles of zinc I have. Notice that for every mole of zinc that I'm plated, I need 2 moles of electrons. Right? So that would give me the number of moles of zinc that I have deposited, and finally, simply multiplying by the molar mass, I can find out what the mass of zinc I have deposited onto that electron. Okay, so the molar mass of zinc is 65.38 grams per mole. Okay, so when you do all of those calculations, you find out that the mass of zinc that you have plated onto that electron in this electrolytic cell when you pass a current of 10 amperes over 30 minutes is 6.11 grams. Okay? Alright, so let me summarize this video. Here we have introduced how electrolytic cells work. It's exactly the same setup as a galvanic cell, but backwards, and what that means is that we are applying an external amount of electrical work to make a non-spontaneous reaction happen. Right? Once we have set up the electrolytic cell, then it's really relatively straightforward to do stoichiometric calculations if you know what the current that you're supplying is.